pyrimidines. I think that's what we were looking at. Okay. So we pick it up from there. I'll give you the unsubstituted pyrimidine. Okay. This is the unsubstituted pyrimidine. Okay. So what we were saying that right. So what we were saying was that if you substitute this hydrogen, remember we said this is number 1, number 2, number 3, number 4, number 5, and number 6. Okay, this is 5, this is 4, this is 3, this is 2, this is 1. So if you substitute this hydrogen at position number 4 with an amino group, so we put an amino group there. Okay. Put an amino group there. And at position number 1, we said that you substitute with an oxo group. Okay. Then we said that we balance off in terms of the valencies. So here nitrogen has a valence of 3, but it has how many? 2 bonds. Okay, so we can put a double bond there. Of course, it has a lone pair. Then you can put a double bond there. We can't put anywhere else. And then nitrogen has 2 bonds, so we can put hydrogen to balance off so that it has a valence of 3. Okay, so we said in terms of naming. Remember, this is position number 1, position 2, 3, 4, 5, and 6. So we are saying that at position number 4, we have an amino group. Okay. At position number 2, we have an oxo group, pyrimidine. Okay. The common name of this one is cytosine. Cytosine. Okay, that's one example of a substituted pyrimidine. But if I decide to do something else, at position number 4, I substitute a hydrogen with the oxo group. I put an oxo group there, and then, of course, there's a nitrogen there. Then at position number 2, again, I put an oxo group. Okay. Then I balance off. This can't have a double bond, so I put a hydrogen. Of course, it has a lone pair. Can't be a double bond here. I can put 1 here. Okay, this must have a valence of 3. It has 2 now, so I put a hydrogen, and of course a lone pair there. Okay, so what I have done then is that I've introduced an oxo group at position number 2, but there's also an oxo group at position number 4. So we are saying there are 2, so we'll use the prefix di. Di what? Dioxo. We have put the oxo group. So 2,4-dioxo, the parent name is pyrimidine. Pyrimidine. Okay. Common name for this one is uracil. And normally we use the common names, easy to deal with. Okay, and the UPAC names. Then the third one, again going back here at the position number 2 or position number 4, we substitute with an oxo group, the same way we did with the second one. Then at position number 2, we also substitute with an oxo group. And then hydrogen at position number 5 is replaced with the methyl group. Okay, so that if you balance off, we're going to have a hydrogen there, a double bond there, a hydrogen there. Of course, these have a lone pair. So in terms of nomenclature, we are saying at position number 5, we have the methyl. At position number 2, And at position number 4, we have oxo group. So dioxo, of course, it is a pyrimidine. Pyrimidine. This is commonly known as thiamine. So these are the common, or let me say, these are the major pyrimidines that you will find in nucleic acids. Okay, these are the major pyrimidines. Okay, these are the major pyrimidines. Okay, but it suffices to say that they are also what are known as the minor. So we've talked about the major, but there are also other bases that are called the minor pyrimidines. What are minor pyrimidines? Minor pyrimidines, we can say, are modified major pyrimidines. So if you modify a major pyrimidine, you modify it in one way or the other, what you produce is a minor pyrimidine. Okay? The major modifications that have been known, okay? The major modifications that are known to exist in DNA, for instance, includes alkylation, or let me say methylation in particular. Okay? Methylation of some pyrimidines. Okay? Some pyrimidines can be methylated. Okay? Others may be hydroxymethylated. Sort of, you methylate it and then you hydroxylate the methylation itself. Okay? Those are commonly pyrimidines that you may find existing. But these are called the minor pyrimidines. Okay? So let me just give you one example of a minor pyrimidine. Let me say, if I pick cytosine. Okay, this is my cytosine. Just looked at cytosine. This is our cytosine. Okay, this is our cytosine. The cytosine, sorry, this is not cytosine. This is cytosine. Okay, cytosine may be methylated at position number 5. Okay, cytosine is without the methyl group. But if we decide to methylate at position number 5, okay, then this becomes a minor pyrimidine. A minor pyrimidine is a modified major pyrimidine. Examples of modifications that are known: methylation or hydroxymethylation. So how would we name this compound? So in naming minor pyrimidines, you look at what is the modification. The modification is the methyl. At what position is the methyl? At position number 5. So we'll say position number 5, we've carried out methylation. What is it? The parent name, it's cytosine. So we'll say 5-methyl cytosine. That's a minor pyrimidine. If we methylate and hydroxylate, for instance, okay. Never forget the lone pair. So we methylate and hydroxylate. So this must be methylene carbon. Okay, methylene carbon. So we would say that at position number 5, we have hydroxymethylated methyl cytosine. This is another minor pyrimidine. Okay, minor pyrimidine. Okay, enough about pyrimidines, major and minor. Now let's look at purines. Let's look at purines. Okay, just in case you've forgotten, we defined purines as 9-membered nitrogenous bases. Okay. Examples. Well, let's look at examples. Right. Before I write the examples, I want to remind you, or let me ask you, what is the name of this structure that I'm drawing? What is the name of this structure? Or maybe I draw it differently. You students, you get lost with orientation if I draw something like this. Okay, but of course, not forgetting that there is a nitrogen there, there's a nitrogen there. Just like there is a nitrogen here, there's a nitrogen here. Okay, what compound is this? What compound is this? Keep in mind that if you want, you can draw this like this. Just want to make sure that you understand what I'm drawing. If I want, I can draw like this, put a hydrogen there. It's still the same structure. Okay? But it commonly exists in this form. It commonly exists in this form. That's the most stable one. In fact, let me draw that one. What is the name of this group? How can you forget? This is the imidazole. Imidazole group. Okay, this is the imidazole group. Okay, right. What is the name of this structure I'm drawing? Okay, that's the name of this structure I have drawn. I'm sure you are going to get lost. Or what's the name of the structure I'm now drawing? If you look at this and this, are they the same? Yes. We just looked at this one. This is the pyrimidine, the parent pyrimidine. If you turn it, it faces the other side. It's this one. Okay, so this and this are the same. It's just that this one has the nitrogen facing to my right, this one has the nitrogen facing to my left. So they are the same. So I just wanted to remind you that this is pyrimidine. Okay, so you have pyrimidine and imidazole. Fuse them together. Put them together. Fuse the two rings so that you form a bicyclic compound. Okay? If you fuse them together, you have the nitrogen there and the nitrogen there. The hydrogen there. Okay? I bring now my pyrimidine there. Remember there is a nitrogen here. That's my pyrimidine. That's it, double bond there, and a double bond there. Okay. Okay, so I have a bicyclic compound made up of imidazole and pyrimidine. Okay. what I produce is a purine. So a purine is a bicyclic compound that is made up of two rings, namely the imidazole and the pyrimidine. So this is a parent purine. Okay? Right. How do you name the parent purine? So in terms of naming, you start with this nitrogen. You start naming with the nitrogen that are on the pyrimidine. And you start with the nitrogen that is far from the imidazole. This is just one carbon from imidazole. This is 2 carbons from imidazole. So the one which is furthest is this nitrogen. So you start on this nitrogen and start going towards the other nitrogen, making sure that the other nitrogen has the least possible number. If you go in this direction, it will have a high number. So this will be position number 2, 3, 4, 5, 6. So you number all the atoms in the pyrimidine ring. After you've finished, that's when you go to the imidazole. So from here, you go to number 7, number 8, number 9. Very simple. Okay? So that's how you number the pyrimidines. Sorry, the purines, I'm sorry. Now, what you find in nature are not the non-substituted. This is a non-substituted purine. What you find in nature are the substituted purines. So let's look at the substituted purines. Okay? Just to remind you, list you have forgotten, here there is a hydrogen, here there is a hydrogen. Okay, remember this is carbon, it must have a valence of 4. So 1, 2, 3, 4. Here there is carbon, it must have a valence of 4. 1, 2, 3, 4. So the bonds are 4. So there must be a hydrogen, which is hidden, which is not shown. Remember in the skeletal structure, we don't show the hydrogens. Right. Now at position number 6, I decide to substitute the hydrogen which is there with an amino group. So I am drawing that structure with a substitution of the amino group at position number 6. Okay, there's a nitrogen there, there's a nitrogen there, okay, there's a double bond there, there's a double bond. Here we introduce an amino group. Here there's a double bond, here there's a double bond. Each of these has a lone pair. Okay. Now this nitrogen must have a valence of 3. It has how many bonds now? 1, 2. So it's not complete. So we can put hydrogen there. Now it's complete. So what have we done to the purine? Sorry for that. What we've done to the purine is that at position number 6, we have introduced an amino group. So this will be 6-amino purine. 6-amino purine, which is called the adenine. That's a common name, adenine. Okay. Right. If I decide to make a different substitution, okay, in this case I decide to make a substitution at position number 2 and position number 6. So at position number 2, I introduce an oxo group. Sorry, at position number 6, this position, I introduce an oxo group. At position number 2, I introduce an amino group. Okay, so what do I have if I do that? Okay, I have a double bond there. Okay, there's a nitrogen there. There's a nitrogen there. So at position number 6, I've introduced an oxo group. An oxo group. At position number 2, I've introduced an amino group. I balance off the valences. Okay, this carbon has 4 already. This nitrogen, must have 3. Okay, this nitrogen must have 3. So if I put a double bond there, then this nitrogen has 4. That's 3 now. 1, 2, 3. this hydrogen has 1, 2, so it must have another hydrogen there. Okay, this nitrogen has 2, so it must have the hydrogen here. Okay. Okay. Right. First there's a lone pair here, there's a lone pair, there's a lone pair there. There are 2 lone pairs there. Okay, so what have we done? What we have done is that at position number 2, we have introduced a amino group. At position number 6, we have introduced an oxo group. The parent is purine. Okay, that's the IUPAC name. This is called the guanine. This is called the guanine. That's a common name, and that's the one we use commonly. So these are the major purines. These are the purines that you find in nucleic acids. Okay, these are the purines that you find in nucleic acid. Okay, right. Okay, right. Okay. Now, let's proceed. So we've looked at the 3 components. We have looked at the phosphoric acid, we've looked at the pentose sugars, we've looked at the nitrogenous bases. We've looked at the nitrogenous bases. Okay, do these have minor bases? Yes, they do. Okay, they may have minor bases. So the minor bases, for instance, let me give one example of a minor base. Minor purine, a minor base, form of minor purine. So we can have, for instance, this amino group can be methylated like that. Okay. In that case, this is a minor purine. But how do you name such? To name a modified base in which the modification is on the atom or on the element that is outside the ring, this is an exocyclic atom, then we need to state where it is connected. Where is this modification connected? It is connected at nitrogen. Okay? At what position is this nitrogen? It is at position number 6. Then we'll say methyl what? Adenine. That's one example. Okay. I want you to contrast the nomenclature there with the one I gave you earlier. So let's look at cytosine once again. This is our cytosine. Okay, excuse me. Our cytosine. Okay, we said this cytosine can be methylated. Where is the methylation taking place? It is taking place on the carbon that is within the ring. Okay, so we would say that this is endocyclic atom. This carbon is endocyclic atom. It's within the ring. So in naming this, you just state at what position has this methyl group been attached. It has been attached to position number 5, the methyl cytosine. Now, in this case, the methyl is attached to an atom or to an element that is outside the ring. So you need to state this atom. Which atom is it attached to? It is attached to nitrogen. Okay, so this someone can see that. So this methyl is attached to nitrogen. So we state nitrogen, the element nitrogen. At what position is this nitrogen? Position number 6. Then you put the group methyl adenine. Okay, that's enough about it. That's enough about it. The purines. The pyrimidines. So now the purines and the pyrimidines can react with our pentoses. Okay, remember we said the pentose that we find in the nucleic acid, there are two types. Okay, which type do you remember? I know you're going to say ribose. Okay, but which ribose do you find commonly? Which configuration? We said the beta configuration is the one that is highly found. So I'll write the beta configuration. How do you know the beta configuration? The numeric hydroxide must be pointing in the same direction as the terminal hydroxide. That's all. Okay, remember the hydrogen here, which I'm not showing. I'm just showing them in case you forget. So this is a ribose. It can react with the, let's say, cytosine. Okay, let's start with the one we started with, cytosine. So this is our cytosine. This is our cytosine. So we can have a double bond there, we can have a double bond there, we can have a hydrogen there. Okay, one pair there, one pair there. Right. A sugar, we know, can react with a sugar, but we also know a sugar can react with a non-sugar. So what is going to happen is that this sugar can react, this hydroxide at numeric carbon can react with this hydrogen at position number. What position is this? Remember we said this is position number 1, 2, 3, 4, 5, and 6. Okay? And this we said this is position number 1, 2, 3, 4, 5. So the reaction can be at any of the hydroxides. But the most reactive one is the one at carbon number 1. The most reactive hydroxide among these hydroxides is the one at carbon number 1. Okay? Right. So when these two react, the water is lost. Okay, the water is given out and the two compounds get condensed. So this is a dehydration reaction in a way. We are losing water. It's a dehydration reaction. Okay, but the two then combine. So let me put what is now formed. So I'm writing my sugar. That's my sugar. I'll not include the hydrogens. Now that you know. Okay, I'll write my terminal CH2 hydroxide there. Okay. Now this nitrogen is bonded to this carbon. Because remember the hydroxide is gone. So, for clarity's sake, I want to use a different color. So, this is bonded to nitrogen. Okay. Then we have another nitrogen there. In that manner. So, we have an oxo group there. Okay. We have an amino group there. Of course, we have a double bond.